Hi, in this video I'm looking at simulating a normal distribution with mean 30 and standard deviation 7 with a sample size of 50, and a binomial distribution with n trials, probability of success of 0.8 and a sample size of 50. And we're going to draw the graphs, calculate the mean and standard deviation of those distributions, and generally comment on the results. So let's have a look at bringing up our graphics calculator. I'm going to be working with a CASIO CG-50, and we're going to use our spreadsheeting application of this calculator. So I'm going to fill out our rules for both of these first. I'm going to do the normal distribution in column A and the binomial in B, and then we'll do the graphs. And my only reason for doing this is just because it will make the calculations a little bit quicker, and it stops it continuously generating random numbers all the time. So just a quick reminder, the normal distribution function with the CASIOs, we have a ran norm number function, and this generates a list of numbers which has a standard deviation, a mean, and a sample size. So we've got to give it the standard deviation first, so we would put in 7, followed by the mean, so we would put in 30, followed by the sample size, which is 50, when we put it into our calculator. For the binomial distribution, the CASIOs have a ran bin function, which takes n, p, and the sample size. So it takes number of trials, probability of success, and sample size. So we would put in 35.8 and 50 when we put into our calculator. So let's go and do these now. So if we bring up our calculator, we've got our two functions here that we're going to put in. So in the first column, column A, I'm going to put in our random norm. So we're going to go shift equals, and we're going to create up a mean. So the random norm gives us a list of 50 numbers, well in this case 50. So we're going to end up summing that. So I'm going to do our sum first. So we're going to go to our list and find sum. And we're going to sum up. If we go back to option, our probability, random numbers, we want a normal distribution list, and we're going to put in a standard deviation of 7, a mean of 30, and our sample size of 50. And because we want the mean, we're then going to divide by how many things are in that list, which is our sample size of 50. And so that generates one random normally distributed number, and we want to do the same for our binomials. So we're going to go shift equals, and we're going to go option list round until we find sum of option probability random. This time we want binomial, and we're going to give it our n, our p, and our sample size. And of course we're going to divide by our sample size so we get the mean. Press execute, and it thinks about it for a bit, and now we have our binomially distributed random number beside our normally distributed random number. And notice that our normally distributed random number changed. That's because every time we put a new change into our spreadsheet, it updates everything. So we got a new number. So now we need to get these to be multiple times because we want a sampling distribution. That's what we're after. At the moment we just have one sample from each of these. So that means we have to figure out how many samples are we going to have. And the bigger the better. So we're going to clip our first rule, and I'm going to go to edit and fill that all down column A until we get to, let's do 100 samples. And so we'll do that one, and it'll think about it for a little bit. Might take a little bit of time considering we've got to do 50 numbers in each sample, and we're doing 100 samples. So now we have our 100 samples of means from our normal distribution. So let's exit out of that and go over and do the same for our binomial. So we go Shift Clip, Edit, Round to Fill, and we'll do the same. We'll do 100 samples. Execute, execute, and we're going to have to wait even longer this time because it's going to regenerate all of our normal distribution numbers as well as our new set of binomial distributed numbers. Okay, so now we have our two distributions. We've got 100 samples of normally distributed numbers with means of 30 and standard deviations of 7. And we had 50 in each. And we've got the same with our binomial. We've got 100 of them. And so let's go and have a look now at these graphs. So we'll go around to our graph menu and we'll have to set up our graphs. So graph 1, I'm going to set up to be the histogram of our normal distribution. So we need to make sure it goes from A1 up to A100. And for my second graph, graph 2, I'll make it be our histogram for our binomial. So it's got to go from B1 up to B100. And so now I've set up my two graphs, I can grab graph 1. And we'll need to think about what we're going to put into our histogram settings. So let's just quickly exit out of that. Let's have a look at what numbers we've got happening here. I've got numbers ranging from about 28 going up in decimal numbers. And I've got numbers over my binomials going up in about 20, from about 27. So let's do our first graph. So we're going to start at 28 and we'll go up in 0.1s. Let's have a look at the graph we get. Looks pretty reasonable. Let's just exit out and graph 1 again. Just make sure there's nothing below 28. Oh, there was a few numbers below 28. So it's a good thing we decided to do that. So we'll grab that graph. So that's our normal distribution. And let's now grab graph 2. Let's first have a quick look. It's got numbers starting at about 27 as well. So we'll go from 27 up in 0.1s. And we'll grab that graph as well. So that's our binomial distribution. So we can now see that our binomial distribution and our normal distribution both seem to be approximating a normal distributed curve. I can grab our statistics for both of these, so I'll do that as well. So that was my binomial because I hadn't changed that yet. So we'll just make sure we can see all of this information. We'll go back to our first graph and we'll grab our statistics there as well. So now I've got our graphs and we've got some statistics. So we can see, if I want to write these down, that for our normal distribution, so for part A, if I have a look at part A, we've got an X bar of 29.98. So our mean is 29.98. And our standard deviation S is 0.95. So our sample standard deviation is 0.95. Now to compare that properly, we'll actually have to have a look at finding our standard deviation properly. And so that means that I've got to actually look at finding my standard deviation of my sample size from my population. So that means I've got to have a look at the rule, which is that our sample standard deviation is expected to have a standard deviation of the population standard deviation divided by the square root of the sample size. So we'll have 7 divided by the square root of 50. So we expected to have a standard deviation similar to that. So we got 7 divided by the square root of 50 of 0.99. So we've got a 0.99. So it's a little bit off, but not too bad. And if we do the same for part B, we've got our one variable statistics, we've got a mean of 27.96. So mean of 27.96. And we ended up with a distribution, a standard deviation of 0.31. So we've got a standard deviation of 0.31. But we've got to do a little bit more work to get the standard deviation we are after. So our population mean that we were expecting here is going to be given to us by doing our n times by our p. So we get 35 times by 0.8. So we're expecting a mean of 35 times 0.8 of 28. So we're not that far off. So of 28. And we need our population standard deviation, which is given by the square root of n times p times 1 minus p. So we're going to have the square root of 35 times 0.8 times by 1 minus 0.8. And so if we go and chuck that into our calculator here, we've got the square root of n times p, which we just worked out was 28, times by 1 minus 0.8, which is 0.2. So we're expecting a population standard deviation of 2.366, which is 2.7. And then if we go and put in our expected 2.37 over the square root of 50 and grab our calculator, so if we divide this by the square root of 50, we got 0.33, 0.33. So if I have a look at our comparison now, so for our normal distribution, we were expecting to have a mean of 30 and a sample standard deviation of 0.99. We got a mean of 29.98, which is very close, and a standard deviation of 0.95, which is 0.04 off, so it's not too bad. And for our binomial distribution, we were expecting a mean of 28, and we got 27.96, so that wasn't too bad. And our population standard deviation says that our sample standard deviation should be 0.33, and we got 0.31, so pretty good. So our sampling of 100 samples gave us pretty good statistics. Our samples were pretty close to the expected from our population. And so we can have a look at our graphs though, and they are both normally distributed. And that's one important thing to note, is it doesn't matter what the original sample distribution is, whether it was normal or binomial or uniform or triangular. When you go and calculate the sample means over a large number of samples, then the graphs, the sample distribution looks like a normal distribution curve. So that's it. We're done.